Hi everyone. So we are gonna talk about some properties of functions in this video, and I will also talk about some kinds of functions which we will keep seeing during these derivative and integral business. So first of all, functions have a property that functions, actually all functions pass the vertical line test. So what is vertical line test, by the way? Let me write this down. So the vertical line test is a curve in the xy plane is the graph of a function f of x if and only if no vertical line intersects the curve more than once. So let me give you some examples here. For instance, let's say we have uh, xy plane. Remember, x is the domain line, y is the range line, or x is the domain axis, y is the range axis. So let's say we have a graph like this. Now, when you have a graph like this, and let's say this is the graph of some relation f, if you look at this graph, it intersects every vertical line only once, just one time. So this is a graph. This is the graph of a function. So f is a function. But if we have something like this, so this is y, let's say this is x, but the graph is something like this, let's say. Now, you see the last part of the graph. If you draw a vertical line, it passes more than once. So this, let's say this is the graph of G. Well, in this case, G is not a function. Because of these intersections here. Okay. So this is vertical line, and all functions have a graph which pass this vertical line test. If the graph you see on the xy plane doesn't pass the vertical line test, then it's not a functions graph. Okay, so this is something we should keep in mind. And then the next thing is I'm gonna okay, let me add some pages first. Okay. Now, the next thing I'm going to talk about is the piecewise defined functions. So Well, these are also types. This is a type of function which we will deal with a lot. So that's why it's important for us, and I should talk about this kind of function. And so these are uh, these kinds of functions are defined by different formulas in their domain. Okay, so let me give you an example. So let's say we have some function like this. Let's say x plus 1 if x is less than or equal to 0, and let's say x squared if x is greater than 0, let's say. So if we sketch the graph of this function, we will see something like this. So let's say this is x, this is y-axis. Now, before x, so this part is from minus infinity to plus infinity. This is where 0 is. Okay. Again, this is from minus infinity to plus infinity. So before 0, which is this part, so this part is x less than or equal to 0, and this part is x greater than 0 part. So for the first part, it's the uh, line x plus 1. So if x is 0, then it's going to map to 1. And then if x is minus 1, it's going to map to 0. And since it's a line equation, it's just going to pass through these 2 points. And it's going to go like this. But if x is bigger than 0, then it's going to be mapped to 0. But I keep an open circle there. And then it's going to go like half of the parabola we have seen before. Okay, so this is x less than 0. It's a line for that part, and it's a part of the parabola for x only bigger than 0. Okay, now I keep an empty circle here because it's not defined as 0 at 0. Because look at this part. If x is 0, still it's x plus 1. So it is equal to 1. If x is 0, 0 plus 1 is 1. So the function gives the value 1. But if it is a little bit bigger than 0, then it's going to give this parabola graph. Okay, so this is a piecewise defined function. We will deal with these functions a lot. Another uh, example that I want to give is something which we will again see quite often. And these piecewise defined functions, you will see them later in the limits. We will deal with them a lot in the limits, in the derivatives, and also in the integrals. Okay, so these are very common types of functions. And what's the deal with them? On some part of the domain, there is some formula. Let's say for the negative numbers, it's x plus 1, but for positive numbers, they are defined as x squared. So they are piecewise defined. And then the other example that I wanted to talk about is this one. F of x equals absolute value of x. So absolute value function. So what is absolute value function? Well, it gives plus x if x is greater than or equal to 0. It gives minus x if x is less than 0. So remember this function, if you put some positive numbers, f of 5 will be absolute value of 5. Well, it's already a positive number, so it's going to come out as positive, or as it is. But if you plug in some negative number, then it's going to give minus minus 1, which is plus 1. Okay, so this is what the absolute value function does, and its graph looks like this. So let's say this is x, this is y. Remember, x is the domain axis, y is the range axis. So for the positive part, it's y equals x. For negative part, it's y equals minus x. Okay, so it has a graph like this, and this is another function which we will again use quite often. Um, okay, and then some other piecewise defined functions are step functions. So let me give an example for that. Well, as you will see, they will have graphs like these. Let's say this is x, this is y, and then the graph looks like this. Okay, so let's say this is 1, this is 2, let's say this is 3, let's say this is 4. Let's give values to these numbers. 0.5, 1, let's say this is 2.4. Okay, so on and so forth. So these are, some step functions, like they go like step by step. They can go higher, take higher values, or sometimes they can take smaller, lower values. But anyway, they look like steps, so they are called step functions. Another property we will sometimes use, it will be useful, is the symmetry. Um, so this is a property that if f satisfies, the function satisfies f of minus x equals f of x, then, well, this is for every x in the domain, then f is called an even function. This will be very useful in the integral business. Like this, just quick example, the absolute value function. This is an even function because it gives minus x, which is plus x, and this is exactly f of x. So it's an even function. There are other functions, but we will talk about them later. And then about this, there is another type of function which will be again useful in the integral. If f satisfies f of minus x equals minus f of x for every number in its domain, for every input in the domain. Then such a function is called an odd function. A very quick example is if we take, for instance, the function x cubed, and then if you look at f of minus x, then the function will take its cube, which is minus x times minus x times minus x 3 times. And that's going to give what? Well, x times x times x is x cubed. Minus times minus is plus, but another minus will be minus. So minus x cubed. But that's minus f of x, right? So this is an odd function. Okay, now another type of function, or maybe that can be called a property, maybe, is the increasingness or decreasingness. So we will deal with this both in the derivative and the integral part. So increasing and decreasing functions. So very shortly, a function f is called increasing on an interval. This interval can be an open interval or maybe some open interval, doesn't matter. If the values of the function are getting bigger if we increase the inputs. In the interval I. Okay, so by this we are actually talking about something like this. Let's say we have some function like this. Let's say this is x1. Let's say this is x2. Then when you look at the values, x1 is smaller than x2, and look at the values. F of x1 is less than f of x2, right? Or you can also have something like this, or just simply like this. In both cases, these are increasing functions. These are all increasing functions, okay? And of course, the other way around is decreasing. Well, f is called decreasing on an interval I if f of x1 is bigger than f of x2 whenever x1 is less than x2 in the interval. So for that, we will have just the opposite case of graphs. So let's say we can have something like this, or something like this, or something like this. Let's see, this is x1, x2 here. x2 is bigger than x1, but when you look at the values though, f of x1 is bigger than f of x2. So then this is a decreasing function. Okay, so and again, we can have three versions of decreasing functions on a basic interval. So this is it for this part.